Hello everyone. Today we'll be discussing our latest technical paper, Tunneling Through 48 Fault Zones and High Water Pressures, Turkey's Gerede Water Transmission Tunnel. Our speaker today is Doug Harding, Robbins Vice President. My name is Desiree Willis, Robbins Public Relations Manager, and I'll be moderating today's presentation, which will be formatted as a question and answer session. And with that, let's get started. Doug, can you tell us a little bit about the Gerede Tunnel, why it's important, and what the water will be used for?
Yeah, thanks, Desiree. This project is a project in Turkey, in Ankara, Turkey, and it was deemed a national priority from the State Department, primarily due to chronic droughts in and around the area. So this tunnel was going to divert a river and then add storage water for Ankara. The tunnel was 31.6 kilometers long, and it required 3 tunnel boring machines, one starting at the inlet, and one starting at the outlet, and one starting at an intermediate shaft. And the machines were 5.6 meter diameter, and the segment, they erected a precast concrete segment. The ID of the segment was 4.5 meters, and the OD was 5.2. This is and still is to this date, the longest water tunnel in Turkey. And the contractor was a joint venture between Colin and Limak. And both these contractors Robbins has been involved with on various projects in Turkey and other places, actually.
Great. And I understand the project had some very complex geology, maybe some of the most complex geology ever bored through in Turkey. Can you tell me a little bit about it?
Yeah, the geology was a fairly remote location through a flat plains area and also a mountain range. The geology consisted of primarily tuff and basalt, but there were on one section, on the inlet section, there was some sedimentary rock consisting of sandstone and shale. The original geology required or found that there might be 30 fault zones around the entire length, but in actuality, when we started to bore, there was many, many more than that. And as we get into this presentation, the section that the Robbins machine bored had 48 faults, and that was 9 kilometers of the full 31 kilometers. So the ground was the geology is much worse than originally predicted.
And the project originally used 3 standard double shield TBMs. Can you tell me a little bit about what happened with those machines?
Yeah, fortunately or unfortunately, the machines were not Robbins machines. Robbins tendered the project, and they were originally specified as double shielded machines, standard double shielded type machines. The machines were in fact delivered from a European supplier. They were delivered at a lower price than what Robbins tendered the project at. And the machines, when delivered, were basically standard double shielded machines, had no capability to do proper drilling and grouting, had no capability to really excavate through these faulted zones. So what happened, as I explained a little earlier, the ground conditions or the geology on the inlet side was primarily good homogeneous rock. So that machine bored around 9.5 kilometers. So it bored all the way to the intermediate shaft where TBM 2 was launched, boring downhill towards the outlet. TBM number 3 was boring uphill towards the inlet, and both TBM number 1 and TBM number 3 and TBM number 2 got stuck. And what the reasons they got stuck is the performance of the machines was good in the good ground, but when it started to encounter the fault zones, both machines got stuck. And what really made TBM number 3 come to the point where it couldn't continue is it bored into a fault zone where we had a big inrush of material, both squeezing ground, trapped the shield, and the machine couldn't advance. They kept turning the cutter head. It eventually excavated into a chamber, which allowed a lot of water inrush and fine materials that basically consumed the machine. Again, these machines were standard type machines, had no capability to seal the machines, and the ground loads themselves actually crushed the shields and trapped the machines.
So given what happened with those double shield machines, why do you think the contractor opted for a crossover TBM for the final section?
Well, after long discussions with, and it was primarily Colin, not so much Lemac, but it was Colin who decided that the double shield machine obviously wasn't a good choice. That same European supplier, his recommendation was to just don't use the TBM number 3 tunnel, which we already bored in several kilometers, and just start another tunnel parallel to it and decommission that tunnel. Robbins' approach was we already had several kilometers of good tunnel already excavated. Let's figure out a way to take the tunnel that's already excavated and continue on in that same alignment. So what Robbins decided to do is that we had good success with these crossover type machines, primarily on another project in Turkey with a different Turkish contractor. It was called the Kargi project. So Robbins used some of that experience. The Kargi project was also a double shield machine. It ran into trouble, but it finished the job after modifications, which included a lot of these crossover features. So what Robbins proposed is to add a crossover features to a new machine. We would then, because the TBM number 3 was essentially not usable, we decided to use the backup system from the machine that was already there and introduce a new head or a new front end of the machine, basically a whole TBM, with a crossover concept that include a lot of special features that will let us get through this faulty ground and the ground that we know is there. So that was the whole premise behind using this crossover type concept.
And can you tell me about the crossover machine? What is it and how is it designed for the ground conditions?
Yeah, the crossover machine has several features that allow us to excavate these bad ground conditions. And again, this comes from let's say historic problems Robbins had and introduced solutions to solve these problems. So what the machine has specifically for this Gerede project is we had to build a machine that was closable in case it had another inrush of material. So the machine was designed for high water pressures. The ground conditions itself did not lend itself well to EPB ground because it was still rock. It was still not a soil that you would normally use in an EPB machine. What we put a screw conveyor in the bottom primarily to help stop the water, and it gave us the ability to excavate and meter the ground. In addition to that screw conveyor, we could also close the complete machine off. And we were able to excavate in 10 bar ground conditions. Above 10 bar, we would stop, drill, and grout. So the machine was really designed around drilling and grouting procedures. So that was very influential in the machine design. We had to be able to get drilling and grouting facilities on the machine. So the machine had excellent drilling and grouting capabilities that allowed us to treat the ground. It also had a very high torque cutter head. What does that mean? So it had to excavate in high torque mode, so we didn't want to get the cutter head stuck. Part of the problem with the previous machines is the cutter heads got stuck. Once the cutter heads got stuck, the shield stopped boring and the squeezing ground conditions started to trap the shields. So that time frame between the time the cutter head got stuck and the time the machine couldn't push anymore was several days. And so we didn't want to have that several days delay to squeeze the machine. So the machine was designed with real strong shields, also tapered shield or step shields, which allowed us to excavate in the bad ground conditions and the squeezing ground conditions, provided we can keep the machine moving forward. It also had very, very high thrust, super thrust. So should the cutter head or should the shield start to get entrapped, we can induce a very high thrust into the segments and keep the machine moving. But the whole philosophy is just get the shield moving the first 25 millimeters with the super thrust condition, and then push the machine the rest of the way with the main thrust, which also was typically much higher than we would put on a typical rock machine. It had more or less along the thrust natures of an EPB machine. We also had abilities to seal the machine off, like I said. So when we would seal the machine, the main bearing had very high seal capability, the tail brushes, and also the sealing ability around the shields.
And what condition was the tunnel in when the crossover machine assembly started?
So when Robbins arrived, the schedule was something along this nature. The TBM number 3 started boring, and then it got stuck. And the TBM number 1 was still boring, TBM number 2 was still boring, and then TBM number 2 got stuck. So from the time the TBM 3 got stuck and the time Robbins got involved was about a 2-year period. So TBM number 3 was standing still by that time already around 1 year. So during that 1 year, the contractor was negotiating with the owner on how he's going to move forward and what to do. And several different ideas were presented to the owner until the owner finally agreed to introduce a 4th machine. We'll call it the rescue machine. Introduce a different machine concept into the tunnel. And so by the time we made that agreement with the joint venture, another 10 months had already expired, because that's the time it took us to build the machine and deliver it. So roughly 2 to 3 years after the machine got stuck, the rescue machine was introduced. The design of that rescue machine was to allow it to be assembled inside the pre-existing tunnel. As I said prior, one idea was to build a whole complete parallel tunnel and lose the 6 kilometers of tunnel we already have excavated. Our approach was to go in through the already excavated and lined tunnel with the rescue machine and assemble it at the heading. At that time, there was still water inflows of about 450 to 500 liters per second. The contractor could never stop the water. The water kept coming. And it was finally understood that that water was being fed from a river above the tunnel alignment. So there was no way that we were going to dry that up. It was always going to be water entering through the tunnel.
So the TBM had to be transported into the tunnel several kilometers, correct? How was it assembled underground?
Yeah, during this whole time, one of the design criteria was, again, we wanted to put the new machine in through the bored tunnel. It was discussed with the contractor that we'd make a bypass tunnel. It was too difficult to remove TBM number 3 that was already there. So a bypass tunnel was excavated around the TBM number 3, which was trapped. So the design of the rescue machine was to bring it in segmented pieces. Shields were segmented, cutter heads were segmented, and in a assembly chamber underground in the bypass area, the TBM was assembled.
And what were the ground conditions like once the crossover machine started boring?
The ground conditions were as we expected, very typical to the same conditions that TBM number 3 and TBM number 2 encountered. It was still the same rock conditions. The basalt was highly fractured, very high water content, very high water pressure. We did bore at 10 bar mostly every day. At times we got up to 20 bar, where we would stop boring and doing the drilling and grout injection. And the highest pressure ever on several occasions was around 26, 27 bar. So the machine did encounter 20, 26 bar pressure on several occasions, 20 bar on many occasions, and 10 bar pretty much every day.
What would you say was the biggest challenge during tunneling? And was the TBM ultimately successful?
Yeah, the TBM was extremely successful. One of the biggest challenges really was introduction of the machine through the tunnel, because there was a lot of water and a lot of fines every day coming in and out of the tunnel. So the challenge was, and it was very hard on the rolling stock that went in and out of the tunnel. Once we got to the assembly chamber, it was fairly dry because the contractor did an excellent job of sealing off that chamber. However, that water was bypassed through the existing tunnel where TBM number 3 was still at, and that water and fines were still rushing down the tunnel. That was one challenge, was get this machine assembled underground, some 7 kilometers in the mountain, in a very difficult geological formation, because that's where the machine got trapped. So this machine, then the rescue machine, the Robbins rescue machine, we'll call it TBM number 4, it had to excavate from where TBM number 3 got trapped to TBM number 2 was trapped, which was around 9 kilometers. So at this bypass tunnel, the machine bored around 9 kilometers. In that 9 kilometers, it had to excavate 48 different fault zones. And remember, originally in this presentation, we only thought there'd be 30 fault zones along the whole 31 kilometers. Well, we found we had 48 fault zones just in the 9 kilometers the rescue machine bored. Once the machine bored its 9 kilometers, it met TBM number 2, cutter head to cutter head. So at that stage, the contractor essentially took a torch, cut out TBM number 2. We pre-grouted all around that area, left the shields in, and then they installed the segments to complete the tunnel. The other problem that was encountered is the muck was removed by a conveyor system. And the conveyor system was in the crown, and the problem with that is this 2 or 3 year period. During that 1.5, 2 years, the conveyor really wasn't run. So it sat there in a very difficult environment. So once the TBM and that conveyor at that stage was going to be around 14, 15 kilometers long. So we had a lot of faults in the belt. The belt would break, primarily because it just was in bad shape from sitting for that many years, not being run in a very wet environment. So that caused a lot of problem. The rollers were all froze up. That had to be greased and fixed. So the muck handling system was problematic for us. The other problems we were encountering is the material was extremely aggressive. It was extremely aggressive on the screw conveyor. So we had several stoppages to replace the screw conveyor, sections of the screw conveyor, make maintenance on the screw conveyor. There were provisions in this crossover machine to have a screw casing that was unboltable, and sections of the screw flight were unboltable to take out of the tunnel and weld repair or put wear plates on the screw. We originally started with wear plates on the screw, boltable ones. That didn't work out, so we ended up with weldable wear plates on the front section of the screw. And twice we had to actually take the screw and replace the front section of the screw. So the wear was much, much greater than we anticipated. Part of this XRE type machine is we had a single direction cutter head. So we had good muck pickup. Again, it wasn't designed for EPB, it was designed for rock. So we were picking up this very coarse, fine rock chips and dumping them into the throat of the screw. That worked very well. We didn't find extreme wear on the cutter head itself, but we did find extreme wear on the screw conveyor.
Okay. And Doug, maybe you can also talk a little bit about the advance rates.
Yeah, the machine started excavating in the summer of 2016. And it took us about 3 months once the first pieces got to the site, to take all the pieces in, assemble it at the heading, and then hook up the backup system that was already there, modified, connected to the Robbins machine, and then start to excavate. It finished in December of 2018. The average day was around 9.4 meters. The week was 71 meters, and the average month was about 284 meters, which was about half as good as the double shields when they were boring in good homogeneous ground. Those machines averaged, when they were boring, around 300 and something meters a month. However, if you take all the downtime in and the shield entrapments, the excavation rate is much, much, much lower. So those monthly excavation rates that I give you were primarily considering everything. Once the machine started to bore, So once it touched the cutter head of TBM number 2.
Great. And given the experiences on this project, what would you say are the lessons learned about how to get through fault zones and high water pressure?
Yeah, these lessons, and we've learned primarily on many projects, is you've got to pre-plan for all this. That was our biggest takeaway from the Cargill project, is that when you don't have good geological mapping, especially on long tunnels in high ground conditions where you can't get to the tunnel alignment with coring, you've got to consider that you're going to hit high water, squeezing ground, fault zones, especially in geological conditions that you know are there, like in Turkey, like in the mountains there. So the takeaways are you've got to really consider adding these special features at the design stage. Plan ahead. Once you're in the tunnel, it's extremely difficult to start changing the TBM design and start adding these features. These really have to be integrated into the TBM design from the get-go, from the very beginning of planning the TBM, especially the drilling and grouting. Usually these drill and grouts drills or probe drills are added to a standard TBM, and their range of operating is not the best. In the conditions here and in conditions now that we're designing these TBMs, we're really designing the TBM around drilling and grouting, because we find that that's really a significant adder to a TBM design to help reduce the risk of this machine getting stopped. And in this case, two machines of the 3 were entrapped and basically are still there today. So lessons learned are really take precautions from the beginning to install as much of these special features into the TBM as you can. You may or may not use them, but when the day you do need them and they're there, it's a day that, every day that this machine stops is a tremendous amount of money. In this case, 2 machines stopped completely. So that's my takeaway. Really plan ahead and put as many of these special features into the TBM as you possibly can from the beginning design stages.
So what is the most important thing that contractors can do to be better prepared in fault zones and high water pressures?
Yeah, that's kind of dovetailed into my last response, but as from the contractor's standpoint, I think what they can do is really prepare for this, not only with the machine design, but also try to get as much geotechnical information you can to the TBM supplier at the early stages. And look at risk management from a higher level of being that, the extra cost of these TBM features that you implement early may be an actual cost of the project. However, again, if you need those features, you have them. You should also investigate and spend some time with these chemical suppliers and grout suppliers. That stuff's advancing quite quickly as well. And there's a lot you can do with chemicals as far as drying things up or grouting, different polymers you could use to help get the ground glued together. And so that really has to be a tie-in with the TBM supplier and the contractor, using all the latest technologies as far as the TBMs are concerned, drilling and grouting, the drill suppliers, and then also the chemical and grout suppliers, and get everybody on the same page of what we think we're going to encounter, and then have that materials on hand. When you do encounter these things, you have the materials on hand so you can immediately put these materials to use and not have months or weeks in between when you have a problem and the machine is stopped to all these solutions are then put on the job site and introduced into the tunnel.
Great, thank you, Doug. This has been a really informative session. And for our viewers, be sure to check out our other white paper recordings. They'll be released throughout the year on our website, therobbinscompany.com.